Welcome to my little Golang tutorial on the basics of the Go programming language. Today we are going to build a very simple application. That's what you can see here. It's Conways Game of Life. And we're going to use this little example to dive into the basics of programming, particularly in Go. So what you see here is the final result of our exercise, and when we're done you will be able to run this little program and see a bunch of cells who are living and dying from one generation to the next. We're going to address the basic programming structures, and we'll immediately apply them to our program at hand, so you can learn by doing it yourself. You can program along or just follow me and pause the video or do it afterwards. But please make sure to take the theory out of this video and apply it to your practical skills. So just before we start, who is this tutorial for? It's basically for beginners in programming and people who are not that experienced yet, but who want to improve their knowledge. Maybe you've heard some things about basic programming structures, or maybe you're a complete beginner, that's fine too. And on the other hand, people who are interested in the language in particular, so Golang itself, and to have some experience in another language, maybe C, Python, Java, whatever. And yeah, people who want to get to know the language better. If you know a lot about Go, if you're a very experienced Go programmer, you will probably not get much out of this tutorial, but yeah, of course you can decide yourself on what you're interested in. Why Go? Well, I think it's a very interesting language. I like that one of the core aspects is its simplicity and clarity. It's not trying to be a very fancy language or a spectacular revolutionary language, but instead it's taking a very pragmatic approach and applying all the principles from previous languages and software engineering experience that were positive, very positive. And the authors of Go, they don't introduce any features which are not very, let's say, production ready, or features that are lacking some kind of practical experience. Also, there's a lot in programming that can be achieved in different ways. There are several paradigms, several idioms, lots of ways to achieve a similar result. And Go mostly has one or a few ways to do something. You are rarely going to think, oh, I got 10 or 20 syntactical ways of doing that. Which one should I choose? No, in general it's 1, 2, maybe 3 ways you can achieve a specific result, and that's very valuable because it keeps large code bases in software engineering clean and maintainable, which is very important for real-life projects. So now that we covered the the basics about who this tutorial is for, let's quickly wrap up the content. What are we going to cover? We're going to set up a very simple Go project. So nothing fancy here, but just to get you started. We are going to learn about basic structures. These are variables, functions, loops, and if statements. The basic building blocks of a software program. Then after a while we're going to include a third-party library. This basically means we are reusing code that another person or another team wrote. So it's very common these days to reuse existing code, in particular open source code that is free to use from the internet, because we cannot reinvent the wheel every time we are writing a new program. So this is part of software engineering too. And we're going to apply all of these things to our simple project, to Conways Game of Life, which I'm going to explain too, so that you end up with a running application that looks kind of nice and yeah, gives you something to be proud of. Let's start with the basic project setup. What we're going to do is we're going to start at the program creation itself. In case you did not install Go yet, I ask you to go to the official Go page, go.dev, and just click on Get Started and have a look at the installation instructions. It's pretty well documented. Depending on your system, there are several installation packages for Windows, Mac or Linux. And personally, I'm on Ubuntu Linux. I already installed Go. It's not that difficult. You can have a look here at the installation instruction, and it's going to explain to you what you need to do. If you're on Linux, you're just going to download the archive, extract it, move it, and expand your path. And you know that you did it right when you can type Go version in your terminal, and it's printing you the current version that you downloaded and installed, and it works, obviously. If you're on Windows, it's an installer that you can run, and it should be pretty simple, I guess, and afterwards you can verify Go version. So I assume you did that, or if not, maybe you can find another tutorial. There are probably some tutorials out there about installing it. And then we can start with the basic project setup. You can take any editor you like. You probably have at least one editor you're using from time to time. I'm going to use Visual Studio Code here, which is a pretty popular and nice editor. You can also use another editor like a simple Notepad or VI, Emacs. JetBrains also has a great IDE, if you don't mind paying a little. But at this stage it basically doesn't really matter. It's just important that you have an editor and that you start learning about this. So now we got Go installed, and I'm assuming you have an editor. The first thing we need to do for project setup is create a folder where we want to store a project. I already did that. I have in my home folder on Linux I got a Go folder, and there's a basic structure in Go where you got source folder, packages, and binaries, so executable packages. We don't need to dive into the details, but source is the root folder where actual source code is stored. So the code that you're writing or code that you're maybe downloading from the internet and studying. And inside that I got a GitHub folder because I want to upload it later, so you can reference it and have a look at it. And there's my name. And now I got, this is the final solution, but of course we're going to start fresh. So I just created the GOL folder, which means Game of Life. You can basically take any path on your system and just create a simple folder on your drive that you can find again later. So now we're navigating into this folder, and you can see it's empty except for my outline where I just described what we're going to cover in this tutorial. What I'm going to do now is I'm just going to create an empty file. You can do that on Windows, right, with a right click, new file, or Linux, Mac, I guess you know how it's done. We're going to name it main.go. Go is the ending of Go source files. Now I'm going to switch to my editor and open the file. Of course it's empty. And there's nothing in here, so we need to enter some source code so we can actually see something. The first statement is usually the package statement. And the package is a way of organizing source code files. For our simple purposes, we are just going to name it main, and it's basically some kind of, you can think about it as a drawer where you put certain things for organizing them. We're just saying this file belongs into the drawer main. It's a way of organizing project files, which becomes more important the bigger the project is, for keeping a clear overview. Now what next? For verifying that this very simple project runs, what is usually done is we're just going to print something to the terminal, like the famous hello world. What do we need to do that? We need to have an entry point for our program. Go programs have a default entry point, which is the main function. So we're going to create this main function. The function starts with the keyword main, func, and the default function is named main. This is just the standard name, so Go can find your start point of the program. And the body of the function, this is called the header, by the way, which is the name and parameters which we are going to cover later. The body is enclosed in these brackets. And inside the body we can write our instructions for the computer. So what we want to do is we want to print hello world as an output to the terminal. In order to do that, there is another function in the standard library of the language that is called print line. And we can give it the string, so the text we want to print, as an argument, which is basically a passed parameter to the function printline. Similar as main, printline is a function, and we call that function in our own function to reuse this standard function. in order to use it, we have to do an import. An import says we want to include this standard module in our own code in order to reuse it. And it is called fmt for format. It has a function print line. So we need to import it in order to state that we're going to use it. We start with the package name format, and we call the function separated by a dot and pass the arguments that the function needs for performing its purpose. So this is basically our very simple first program. Now let's check if it actually works. I'm going to save the file, Control S in my case. And now we're going to have a look at our folder again. There's our main file. And by using go run, we can run this program. Let's see if we did a mistake or if it runs as expected. Okay, it works as expected. So you can see our string is printed. Let's say I've made a mistake, I forgot something. Let's say I forgot to import the standard package for printing. Save and rerun it. Then I'm going to get an error message. It's going to tell me in file main.go there's an undefined symbol and it's fmt. So it doesn't know what it is, what it refers to. Of course, it's pretty clear that we're missing the import. But in case you're experiencing such errors, you can use the output to debug your program, or ask other people or Google around what the error might be. Usually it's pretty clear what the program is missing when you get such a compile error. Because Go is a compiled language, it will translate our source code, our Go files, to a machine language and then run this machine language, because source code is written from humans for humans to understand it and to extend it. But a machine like a computer needs another representation of these instructions, and that is a binary representation. And the compiler, the Go compiler, translates it from Go language to machine instructions. Okay, so that's our basic program. Strings are encapsulated in quotes, because otherwise the language doesn't know it's a string, so a text, which is basically our first data type that we talk about. Let's say I'm forgetting the quotes, and now the compiler will complain about a syntax error, unexpected word, expecting comma, or the ellipsis. And that's because it doesn't know what it's supposed to be. But when you close it in quotes, the compiler knows it's a text, and I shall interpret this as a text for printing in this case. So that's it. That's our first program. It's a very basic project setup. And now you know how to create a new simple project. Now let's start with diving into the basic rules of Conways Game of Life. We previously set up our simple Hello World project with Golang, and we looked shortly at how to install it, where to find install instructions, and which editors you can use, for example. Now, before we can actually start programming away, we need to understand how this kind of mini simulation works, right? It's called the Game of Life, and we can just have a look at Wikipedia that says it is some kind of cellular automation, and it was invented by a British mathematician in 1970 named Conway, and it's not a kind of classical game and not something like a multiplayer game, but it's a game that starts with a specific state of cells on a grid, and then there's some kind of rules set to follow for calculating the next generation of these cells. So you can see an example here, a pretty fancy example. And the playing field is basically a matrix. So just imagine you get a spreadsheet or a table, and in the beginning there are some live cells on the field, just a few. And by using some very basic rules, we can calculate the next generation of cells. So just to fire up your imagination a little, these cells, they live and die according to a few rules, and these are the basic rules. A cell that has 2 living neighbors or 3 living neighbors will live on to the next generation. But a cell that has fewer than 2 live neighbors dies, maybe as a cause of underpopulation. A cell that has more than 3 live neighbors dies due to overpopulation, so too many neighbors in this case. And dead cells can also become alive if there are 3 live neighbors around it, like some kind of reproduction. So these 4 rules together can be simplified a little, and then you get the same by applying these 3 rules, saying that 2 or 3 live neighbors means the cell survives. A dead cell with 3 live neighbors reproduces and creates a new cell, and all other live cells die in the next generation or stay dead because there are not enough neighbors or there are too many neighbors. Using these pretty simple rules, you can run some kind of simulation or little game that creates some shapes. Sometimes very simple still shapes that don't move at all. You can see some examples here. Or some shapes that do repeated movements like a blinker, or something more fancy like this pulsar. And there are also some interesting shapes that actually look like spaceships from above. And these are just a few examples. There are more of them, and I think that's a pretty fascinating part of this game, that you get very different shapes and very different movements depending on the initial population of cells. It's kind of nice to look at. So just to make sure that we got our rules right, let's apply them to a very basic example so we actually know what we are programming and we understand our goal. Let's say we have a very basic field of just 9 fields, so 3 columns and 3 rules. I just did a simple sketch here. The circles are live cells and the empty squares are dead cells, so empty fields. And let's say we start with a basic population of these 4 cells. Now, by going through each square and applying our rules, we can calculate the next generation of cells. Let's start at A1. There's a live cell and it has 1 living neighbor. 1 living neighbor is not enough, as we already know. That is why it dies, and it's empty in this next generation here. The same is true for this cell, it also dies, and for this, because there's only 1 neighbor. There's this neighbor, but nobody else. But this dead cell becomes a live cell because there are 3 neighbors. 1, 2, 3, A1, B2, C1. And in C2, you can see there are also 3 neighbors, so G2 in the next generation becomes a live 2. And finally, the one in the middle, it stays alive because it has 3 neighbors to the upper left, upper right, and lower right. And we know 2 or 3 neighbors means the cell stays alive. So for a very small grid, we got the next generation. Now let's go 1 generation past that. We repeat the process. We do the same as before. Here on the upper left corner, there are not enough neighbors to spawn new cells, but this one got 2 neighbors, this one got 2 neighbors, and this one, so these 3 stay alive. And this dead cell or empty square has 3 neighbors and becomes alive. So this is our final shape in this case. And you can see that in our example, this shape will stay the same. It's actually a static block because these cells have enough neighbors, they stay alive. And on the outside, there are not enough neighbors to spawn new cells. So this is an example of a static pattern. Let's have a look at a second example just to make sure we got everything right. Let's say we start completely new at generation 0, and these are the 3 initial cells. And applying our rules, again, we see that these 2 cells have fewer than 2 neighbors, only 1, and therefore die. This cell has 2 neighbors and survives. This cell becomes alive because it has 3 neighbors. Yeah. And the next generation, sadly both cells die because 1 neighbor is not enough to survive, and they both become empty squares. And so there's not anything spawning here. Of course, we are going to use a much larger grid because it's more fun than such a small example. But that was just to give you an illustration of our rules, because it's important to know what we are going to achieve with our program. We apply the same rules to a large grid of many hundred or 1,000 squares and calculate one generation after the other. So, now that we understand the basic rules of Conway's Game of Life, we can actually start to program. Going back to our basic project setup, we still have our main function where we call the standard function print line from the FMT package to show our string value, which is basically just text on the terminal. And I can go to my folder from our source file and run run file.go and get my output. Now, what we want to do next is we want to create a first generation of cells. Like in our grid example, we want to be able to have a first generation of cells and store it somewhere. We need to store it in memory because otherwise we can't do anything without it, right? You have to know how our current grid looks like to calculate the next generation and to print it for visualizing. So let's talk about variables first. The need to store data is everywhere, and that's why we have variables in programming. They hold specific values in memory, in main memory, so it's not necessarily persistent, but it needs to be stored while the computer is running in memory. And Go knows the keyword var for variable. So you can declare variable by using this keyword and then specifying a name. Let's say we want to store the count of live cells. So I give it a name of count live cells. And now I have to specify its type. The data type tells which kind of values we want to store in the variable. Since it's a count, we want to store integers, so whole numbers. And the most simple type in Go, therefore, is int. Now that's a declaration, so we created the variable. It's known to the program now. But we also want to assign a value to it. Most of the time it makes sense to have an initial value. And in this case, we don't know the specific number yet, so we initialize it with 0. So that's called the initialization, the first assignment of a value to the variable. You can see these red underline, that's a compile error, and the compiler is trying to warn us about things we forgot or things we need to take care of. In this case, it's telling us that we created a variable that is declared, but it's not used yet. So it says, please make sure to use it or remove it if you don't need it, just to keep the code clean and maintainable. But it's not bothering us because we're going to use it soon. So let's say I'm writing some more code, and somewhere down here we're going to change the value, and we determined the count of live cells is, let's say, 5. So I can use the assignment operator to change the content of this variable. And sometimes later we want to print the count so we can actually see it in the output. So we want to basically write this. But of course we don't want a static 5 in our string, because the program shall also work if, let's say, the count is 10, and I don't want to adapt this output for every possible value, so I want this to be dynamic. What we basically want to do here is to include the value of count live cells, and that can be done in different ways. One way is to use a formatted print function. It's called printf, and then we can insert a placeholder for our value. It's a %d in this case, because d stands for decimal value. It's going to be formatted as a number. The % indicates that this is a placeholder. Now we have to pass the variable. And what this standard function printf is going to do, it's going to read this string and substitute any placeholder with the variables passed here. So let's try it, save our file, and run the program. And you can actually see it's printing count of live cells 10. And just to make sure we got the concept of variables, let's say at a later stage I'm going to add some more code and the live cells count reduces to 7. I'm going to print it again, just copy paste it for simplicity, save and run the program. And it's going to print 10 as before and then 7. Let's add a new line, a line break for better readability. You can do that by writing \n, that's a control sequence that gets interpreted as write a new line. And this looks somewhat cleaner now. Another way to do this is to can also write a print line with an empty string, because print line, as the documentation says, adds a line break at the end. A new line is appended. So it's basically the same effect as writing \n. You can use whatever you like more, but I usually prefer the more compact way of using the control sequence \n. So this is a basic variable. Go has some nice simplification where you can shorten the declaration and initialization part. We can omit the var keyword and the data type and instead write colon assignment operator. And what happens behind the scenes, the compiler figures it out that this is actually a variable of type int, because there's a numeric value on the right hand side. The compiler is smart and knows, okay, you want to have an integer variable. You can keep it short, and I'm detecting it automatically. So this is a shorthand for declaration and initialization. And you can use it most of the time whenever you want. There are some cases where it's more preferable or required to use the explicit format. So just to make sure it works, we run our program again, and we see it's the same output, just with a little less code. So now we know how variables work in a very basic way. There are more data types for variables. Let's say you want to store a string, maybe the color of the board. Then we can call this board color, and to assign a string we use double quotes, and let's say it's green. And this is a variable of type string. Now, of course, we get some compile errors because count live cells is no longer known. We didn't declare it. We replaced it with board color. So let's replace this and adapt the text. Color of board. And this is now a string, so the correct placeholder is S for string instead of a numeric value. And we still have some errors because count live cells is not declared. This is board color. But of course we can't assign an integer value to a string variable, because variables are boxes for data. And when you say that your box stores numbers, you can't simply assign a string. This is actually a pretty useful concept that's called static type checking. It helps to prevent some kind of errors during programming, because the compiler can detect these type mistakes during compile time, and you see the error right now before I'm running the program. And most of the time it's preferable that I'm seeing these errors before I'm using the program in production, let's say, and that's where errors are much more of a hassle than during development time. So the compiler is actually of help in this case. This is one of the benefits of using a programming language with a static type system like Golang, or other languages like, let's say, Java or C. So let's just remove this, print the color of the board, and then change it to yellow. Again, we have to take care to use strings, otherwise we get an error. And finally adapt the second text. Save, run our program. And as expected, we get the color as an output. Okay, so these are two of the most basic data types, strings and integers. For our grid of living cells, we actually want to know if a specific cell is alive or dead, right? So we want to know, is A1 a living cell or an empty square? So we got two values, two possible values, alive or dead. And that's a typical use case for binary values called booleans. So a boolean value, let's just use the explicit form for sake of exercise. A boolean value is, a boolean variable is declared like this, and you can assign two values only. It can either be true or false, nothing else. And this is I would say the most basic data type in programming. So let's replace it. And now we get a warning, that's a yellow underline. And that's, again, the language helping you, or let's say the tooling around the language, because it says bool is a wrong type for the formatter, as %s is for strings. This is a boolean, so we could look up the documentation. Actually, let's do this to get an idea. Golang FMT formatter. We're going to have a look at the package documentation. And that's where you can have a look at for standard functions, how to use them. And there we see here boolean t, the word true or false. And we can also see for strings, you can use s for a string. And there are much more options for formatting output. Just a general tip, if you're not sure about the correct formatter, or if you want a very generic formatter, use the V. V is using a default format. It's basically applicable to everything, although you may see that it's not the format that you wanted, and then you can adapt it at a later stage. So let's try this. Let's try it with the explicit T for booleans. Save and run the program. Works as expected. Prints true or false, alive or dead. And let's use the generic V formatter, which is kind of useful if you're in a hurry or you want a very generic way. You can see this uses the default format, which works just fine. Okay, now that we got our Boolean variable for storing if a cell is alive or dead, we can expand this concept to hold a complete field of Boolean values, because we need to remember all cells on our field. And of course, we don't want to declare and manage hundreds or thousands of variables one by one. We don't even want to do this for 3 times 3 fields, so 9 fields in total. There are better ways to do that. And in this case, we can use a very basic data structure that is basically a list of values. You can imagine this like a list you use for getting groceries, or a list of telephone numbers in your smartphone. It's basically a sequence of values with a similar data type. And in programming, we call the very, very basic kind of list that is stored sequentially in memory an array. Go, of course, also knows arrays. And to give it a better name, let's call it cells. and our data type is an array. As you define it by using these square brackets and saying which data type you want to store in it. In our case, it's a bool. Now, the important thing about arrays is that the size is fixed. So let's say for a very simple example, we need 3 of these Boolean values. So 3 times 3, 9 places to store the Boolean value. And that's it. That's our very basic array. It has a name. It has a capacity of 9 and it has a data type bool. Now we are not using it yet. Let's change that and say print it. And let's see how it looks like when we print this array. We didn't initialize anything yet. We didn't assign any values or change anything. We just declared it. And we can see inside these square brackets are 9 Boolean values. All of them are false. Why false? Because Go has a default value for each data type, and it's called the 0 value, although it's not necessarily a 0. In case of integers it is, but not for Booleans. It's basically a default that is set automatically if you don't specify anything else. So that's pretty useful for us, because by default we mean our square is empty and there's no living cell. Now let's get back to our array and let's say we want to initialize some values. Let's say we want to have this field here, and an array, as you see in the output, is just a list that is where each element is numbered. Most programming languages number these elements by an index that starts at 0. So going back to our output, this is index 0, position 0. This is index 1, 2, 3, and so on until we are at 8. So size 9 means space for 9 elements and indexed from 0 to 9. This is how you can specify which position of the array you want to read or write. So going back to our code, we can say, okay, I want the first value of the first element in the array to be true. And you do that by using the square brackets and saying index 0, assign value true. We're going to see, okay, first value is 0, is true, sorry, and the rest remains false. That's how you address specific values. We can also say we are interested in a specific part of the array. Let's say cell, the last one, cell number 8. So cell with index 8. And then we can't just pass the complete array, but we pass the last one, index 8, save and run. And now we get the output, okay, number 8 is false, it's this element. Okay, that's the basic thing about arrays. So you can just imagine that we enumerate these cells from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8. And in our case, position 0, 2, 4, and 8 are alive, so we want to set these to true. So let's do this. Instead of doing this one by one, we can do it in a single line of code. And it's basically similar to our previous variables. We can immediately use the assignment operator and state the values. Of course, we have to give it 9 values because we said it's size 9. And I can just write them one by one. So let's check again. It's true, false, true. False again, true, false again, 2 times false, and true at the end. Yeah. So let me see, I got the syntax wrong here. Yeah, this is how it's done. And we can shorten it because the compiler knows the data type from the right hand of the assignment. It knows, okay, this is an array of size 9. These are your initial values, and this is your variable name, cells. Now we can remove this and have a look at the output. And we see it's what we expected, true, false, true, false, true, 3 times false, and the last one is alive again. So now we got our initial cell state set up, and we also did a very basic printing. Now let's say we want this to be a bit more visually interesting. It's kind of hard to see which fields we're actually visualizing here. It's just a very abstract representation. So let's say we want to print a 3 times 3 shape that looks a little bit like this. So now that we know how an array works, basically, we can move on to the next basic construct. And this construct is called a loop. Loops are for repeated actions that you want to perform in your program. And you can imagine something like a list or an array is a perfect example for this. We got a complete list of values in this data structure in our variable cells, and we want to do something for every element in this list. without having to repeat our instructions for every single element. So we will use a simple for loop to do our task. In Golang there's only one loop, and that's the for loop. It works like this. You usually have something that you're iterating over, or you have another variable that tells the loop where to start and where to stop. In our case, we are going to tell the loop to start at index 0, so at the first element, and continue looping until we reached the end of the array. So at first you start the loop by using the keyword for. Then we're defining a variable for iterating. It's an integer variable, and I call it index for clarity. I immediately assign the initial value 0 because we want to start iterating at element 0. And then we define the condition of the loop. So the first part, after the for until the semicolon, which is just a separator, we define the initial setup. It's executed once when the loop is entered. Then we define the loop condition. The loop is executed as long as this condition is true. So we can write any expression in it that returns a Boolean value like true or false. Our expression is index smaller than the length of the cells array. This is true as long as our index is smaller than the size. Size is 9, as we wrote here. So 0 to 8 will yield true, 9 and above will yield false. When false is reached, the loop exits and the program continues its instructions after the loop. Finally, we got the update part of the loop, which is index ++, and it means that we increment it. We increase the index value by 1. It's basically a shorthand form for the following assignment. Index is index +1. We could write that too, but this is a very convenient way of writing an increment. So we keep it at that. The update instruction is performed each time the loop executed once. So the body is enclosed in these braces. And now we can write our instructions here. And the execution is as follows. Initial setup is executed once before the loop is entered. Then the loop condition is evaluated. And if it yields true, we go inside the body and read the instructions. Once the instructions inside the body have been executed, index ++, the update is executed, and then the loop condition is evaluated again, and so on. So that is where the name loop comes from, and the repeated instructions occur. Once the condition is false, the loop is exited. This will become much clearer soon when I'm adding the missing code here. So what do we want to do? We want to have a better representation of our board representing living or dead cells. So in the most basic way, we could start by printing the value. We use our known function printf formatted, and we say we want to print the value. I'm going to use the default formatter that will find the correct default representation. And now we have to fetch the element. So we got the index, but we want the correct element. I'm going to use a variable just for illustration purposes. And let's call it cell, because it's a single current cell. And access the array at the current index. It's basically the same as we did here, but we used the index variable, which changes in every run, and not the static value at index 8. Now we got our cell and we can print it. And let's add a new line so we can actually see it much better and run our program. Go run our file, and you can see we ran over the complete array and printed every value inside the array, followed by a line break. And that's the basic power of loops. Even if this is a much larger field with thousands of squares, I don't need to repeat all instructions, but I can write them very compact inside this loop. So now we want to improve our representation that is not very visually stimulating, so to speak. And let's say instead of true false, we want to have something like we did in our sketch, where a circle means a living cell and an empty square looks quite different. So we don't want to print true and false, but we want to print some custom characters. We're going to use an if statement for that. If statements are another very basic building block for programs. And as the loop in its condition, if statements require an expression that returns a Boolean value. So lucky for us, these are already Boolean values, so we just have to say if cell, and then we add the actual branch enclosed in braces, and this is what will happen when the expression or variable holds a true value. If it is false, it is not executed. So let's just rename this to make it more clear. Actually, we should name this alive, because it immediately tells us alive can only be true or false, right? You can either be alive as a cell or not. And this is very clear to read. If alive, do this. So what do we want to print? We print, let's say, an O character for a living cell. That's it. And we can use print line for that to add the line break. Now, what shall we print when alive is false? That's where an else branch comes in. And that's what happens when the if condition is not true, then else is executed. And we want to print representation that is looks more empty. Let's say we use hash. So save our program, run it, and we can see that true is translated as an O and false as in hash. So that looks a little bit better, but we want to have something like this where we actually have columns and rows. So we want to print 3 elements in a row, then a line break, another 3 elements, and another 3 elements. So now we have a very simple representation, but of course we want to do better. So let's create some kind of little grid representation. We need to add line breaks for this after 3 columns in a row. So what we actually want is to execute the loop body 3 times. So for index 0, 1 and 2. And once we are in the 4th iteration for index 3, we want to add a line break before printing. So how can we detect that? We can add another if statement. And let's say index equals 3 or index equals 6. Then we're going to say print line to just print the empty line. So obviously the first one 0, 1, 2 will not run there. The third one will run inside. 4 and 5 will just go directly to the cell printing, and 6 will add another new line before printing the cells. Let's see if we got that right. Yes, so 3 cells per row. Let's remove this. We don't need it anymore. And that's a very, very inelegant way to do it, because we have to specify the specific index, but for our little example it works. We can improve this by finding a more generic rule. So what we did here is we checked for equality. So a single equal sign means assignment. Assign the right hand value to the left hand. And that's how we assign variables, or in this case there's another colon because it's a shorthand for declaration and assignment. But a simple assignment could look like this, as I've shown before. That would be an assignment. So in order to distinguish this from the equality check, so an expression that checks if the left value is equal to the right one, we need to use double assignment operator, and that's the equal operator. This in the middle is a logical OR operator, and that means that a combined expression shall be evaluated. This is the left part of the expression, and this is the right part. Both return a Boolean value. And when you combine them with a logical OR, following rules apply. If one of them is true, the complete expression is true. That means at least one of them. Both lead to true also. But if both of them are false, it will be false, right? So that is logical. Or you want to use that when one condition is enough to satisfy your criteria for the branch. There's another one that's called a logical AND. It's a double ampersand, and that basically means we need both values to be true for the final result to be true. If one of them is false, the complete expression will be false. And of course, two falses will result in false. So, with that being said, we want to use a more generic expression for our if branch. What is the actual condition? The condition is we've reached an index that is divisible by 3 without any remainder. So 3 divided by 3 will result in a remainder of 0. The same is true for index, because you can compose these values by multiples of 3. There's no rest part. This is not true for other values. So we can achieve that by using the modulo operator, which is a percent sign. And of course it needs to be a Boolean expression. The compiler says non-Boolean condition in if statement. Why? Because modulo operator returns the remainder integer. But we can use the equality operator to check if this is 0. And that can only be true or false, so we got our Boolean condition. Now there's a simple mistake here, but let's first see what happens. When we run it, we see okay, that looks pretty nice, but there's a line break right at the beginning. That's not what we wanted here. That's because 0 is our first index, as it is in most programming languages. Some start with 0, 1, with index 1, but not in C-like languages like Golang. So 0 divided by any integer will yield no remainder, but obviously we want to skip this corner case. So what we can do is we use our logical operator AND to skip the first one. We could use index equals 1, but we can index unequal 0. This is the exclamation mark and equal sign. That means not 0. Let's just try this, and that's how it works. So it means index is not 0. That works perfectly fine in our case. What we can use instead, we can say index needs to be greater than 0. And that works too. So now we have a very simple representation of our playing field. And we just did that by using an array variable, a very basic for loop with its three parts and the body. One more variable, a boolean, and using some if statements, including an else, with a little printing and some operators. Okay. So now what we are going to do next. Our next step is to actually calculate a new generation. So for our game to look nice and to actually work, we need it to be somewhat dynamic, right? We want to progress to the next generation, apply our rules from Conways Game of Life, and print the next generation. So we need to implement the logical rules of Conways Game of Life. So let's remember them. The short form is basically consists of these three rules. Any live cell with 2 or 3 live neighbors survives. Any dead cell with 3 live neighbors becomes a live cell. And all other live cells die in the next generation. Similarly, all other dead cells stay dead. That's what we need to implement now. So we go back to our array and we think about how we can add these rules. We have an array that has a single dimension of 9 elements, and it's basically a linear representation of our rectangular field. We could calculate our neighbor positions by using some operators like the modulo operator. But instead of doing that, I want to introduce another concept to you, which can be useful sometimes. And that is the concept of two-dimensional arrays. Now, a two-dimensional array is basically an array consisting of arrays. So imagine instead of true, false, we got another array inside here. So when you look at the illustration, these 3 elements would be one array. These 3 in another row are another array, and the third. So you can imagine a two-dimensional array as some kind of matrix or a table consisting of columns and rows. The outer array represents the rows and the inner array our columns. So how do we declare such a two-dimensional array? This is another data type. So we add another pair of brackets and we specify its size. So 2 and closing brackets means it has 2 dimensions. Each dimension has a size of 3 elements for our simple case. So now we change the type and we get a compile time error because our initial values don't match the type anymore. What we actually want is 3 smaller arrays. And we can do that like this. So the inner array is our row. So this is the first row, this is the second row, and this is the third row. And the outer array is basically the container for these rows. Now we have to change the way we're iterating a little bit, because we are no longer running over a data structure that directly contains booleans, but we're running over a data structure that has an array as its content. So to make this more clear to you, you can see here when you hover over it, the type changed. It's no longer a simple bool, it's another array. So to make this more explicit, let's call this row and write the type just for clarity. No, it's just saying we didn't use it yet. So once we enter the loop, we got a complete row from the outer array. And now we want to iterate this row, the cells in the row. And you guessed it, you can do that by using another loop. So I'm going to use another loop, and let's call this column. Just going to use a call. Iterate as long as we are within the bounds of our row length. And then we can add our printing code. Move it here. And alive means we need to get the Boolean value from the inner array, which is row at index call. Okay. And now we can simplify our line break logic by saying once we completed the whole row, we know we need a line break. So we can simplify that and just say, after you're done with the row, add a new line, right? Line break. So we applied the same principle as in our first loop. Now to make this a little bit more clear, let's change the name from index to row so we can better remember where we are in the matrix. So row is our row index and call is our column index from the inner array. Well, let's see if this actually works. Save the code and run it, and as you can see, we got the same result. Now you're probably saying, okay, but we didn't achieve anything yet. It's the same output as before. Yes, you're right. We changed the data structure from a simple one-dimensional array to a two-dimensional array. But now it becomes a little bit more clear to us how to determine the neighbors of a cell in order to let them live or die accordingly. So what we need is we have to look at our current position and then at the neighbors. So let me go back to my illustration. We are going to start in the first row in the first column, then go to the next column, go one row down, first column, second, third column, and so on. And during each of these steps, we look around to the neighbors. So when we're here at B2, we look at every single of these 9 neighbors. So we need to add or subtract a row or a column index to get to all neighbors. Moreover, we need to handle these corner cases where we are already at the edge of the playing field and there are no more neighbor fields on the left or top side. So this is something that we need to take special care of. Now let's calculate the next generation. What we basically want to do is we want to determine how our new variable on tcells looks like. So you can imagine it's also a two-dimensional array which has the same size. But we actually don't know yet how it will look like. So it's not an initialization but a declaration. And the default value for booleans is false. So initially this will be a two-dimensional array with false values. We can verify that by printing it here instead of cells. We are going to use tcells. Cells declared but not used. Okay, that's the compiler telling us we shouldn't leave variables unused. So I just made a comment out of it. When you want to comment your code, which can be pretty useful for explanations that are not immediately visible in your code, you can just use these double slashes and the line will not get interpreted or compiled. It's just a comment for the human reader. Okay, and now we see it's a completely dead field. All values are false. So let's go back. This is our cells field. Let's call it first cells because it's our initial set. And we want to calculate nextcells. So let's revert this. We are still iterating over first cells. And at first the rows, then the columns. But now instead of printing, we want to look at the neighbors. So I'm going to remove that and we basically want to have something like this. The neighbor count. And I'm just going to write a function that doesn't exist yet. And depending on the neighbor count, we can now implement our rule set. Conways Game of Life says if the neighbor count is 2 or 3, remember our equality check operator and the logical OR operator, then the cell stays alive. So we say next cells add row column. It's the same position as we are now in our first cells. Array is set to true, meaning alive. So this is rule number 1. Any live cell with 2 or 3 live neighbors survives. Now, of course, we have to check if the cell is actually live. So, guess I shouldn't have removed this. And you can see a 2-dimensional array is addressed with 2 pairs of brackets. The first is the outer array index that we want, and the second the inner array. For 2-dimensional arrays we have to specify both, because otherwise it's not clear which inner value we want. So, what does the compiler say? Index row must be integer, of course, because I can't just say this. I have to take the row. We already got the row up here. It's a single dimensional array. The inner array, so to speak. And now we can determine the inner value. But that's not row, because we want to set the new array. So, still some compile error. And that's because we did a mistake here. We used the same variable name twice. So that's something that you should avoid. I took the row name for the outer array index, and then I used the same name for the actual row, which is not a good idea because it's basically shadowed now. At this point it's no longer the variable from above. So what we do instead is we call this row index. And we call the inner index, call index. So there's no naming conflict between our variables. Now let's have another look at this inner loops condition. We iterate for as long as the column index is smaller than the length of the row. And that's perfectly fine here. So what we could do instead is we could shorten it and directly access the two-dimensional array from our first cells. So instead of unpacking the first array here, we can say use first cells. Then we don't need this intermediate step. Of course, they also have to replace the length check. And this time we're just going to access the first dimension of the array, because we want to get the inner array and iterate over it. So just one pair of square brackets. Okay, got it. Now we have the first condition. We need to check if this cell is actually alive, and neighbor count needs to be 2 or 3. Another very important concept is the order and the priority of these Boolean expressions. The AND operator has a stronger binding. Let's say it has a higher priority for the program than the OR operator. So what actually happens is alive, and alive can be true and one of these can be true. But when neighbor count does not equal 2, we got true and false. And only afterwards, so this is evaluated first, and then comes neighbor count equals 3. So it's basically like this. The parenthesis part is evaluated first by default, because the AND operator has a high priority per definition, and then comes the OR part. But this is not what we want, because it means even if alive is false and this is false, we can still get a true for the complete expression, because the OR condition is evaluated at the end. So we could have the case that neighbor count is 3, but the cell's dead, and it will yield true anyway. We don't want that. That's when you need to specify the priority yourself. So by using parentheses around the OR condition, you say evaluate this condition first, it has a higher priority, and then the AND connection. This is what we actually want. We want to check the neighbor count in and of itself and then combine it with our alive check. But of course, if the cell is not alive, we don't even need to look at the other condition. That's what our construct is about here. So I hope this is more clear now, and we can add another rule. Any dead cell with 3 live neighbors becomes a live cell. So we can do that with an else. And what you can do is you can add another if. So this is what we did during printing, right? We just said else. When if does not apply, do whatever I write here inside the else block. But we want it to be a little bit more specific. We don't want to do it under any condition, but just else if we're not an alive cell. Not as the negated Boolean result. So false becomes true and true becomes false. And it can be expressed with an exclamation mark in front of the Boolean value. So when we're a dead cell and our neighbor count is exactly 3, then we become a live cell. So next cells at this same location becomes true. And condition number 3, all other live cells die in the next generation. Similarly, all other dead cells stay dead. So we can say final else branch that needs no further specification. That's when we say becomes false, dead. Now these are our 3 rules. This is, let's add some comments actually to remind ourselves and other readers about the intention behind it. Yeah, that's it. So we could say we don't really need the last else branch because our next cell's values are false by default. So we don't need to overwrite any living cells. But remember, we're programming this for the complete game ahead. So in further iterations and generations, we will have the case where living cells need to die. And actually, what I just said is not completely true. We already have that case here. You can see it here when we start that pattern. You need to eliminate this living cell as well as this and this. So you definitely need this else branch. Okay, now to check if this actually works, we need to print again, and we need to implement the calculate neighbor count. So what we can do first, since we don't want this to be too long without any feedback, we add the printing again, but just after our loops, right? So we say for row index, col index, if next cells can just write it directly because the result is a boolean for alive or dead. And the line break down here. And you can see our code is already getting a bit messy. So let's create a new function for keeping it nice and clean. We're going to call it print cells. We pass the array as a parameter, and that's a way of giving data to a function. So we can move that code here, nicely encapsulated, and instead of our variable we now use the parameter, which is some kind of variable, but it needs to be passed to the function when we call it. So now we can call the function, and that's done like the format function, for example, but it's our own function. We can just call it like this, print cells, and the compiler says not enough arguments because we need to satisfy the parameter list. So we want to print next cell, so we pass it as a parameter. And the nice thing about function is it makes the code more clean, and you can reuse them without repeating the code. So we can start by printing the first generation of cells, and then the same without much effort, which is pretty neat, right? I'm going to add a line break in between so we can differentiate. Or let's just use yeah, that's okay there. And now we just have to do something about the neighbor count to actually see something. Before we implement the neighbor count, that's a story in and of itself. Let's do some pretty basic dummy result here. And we're just going to say, I'm going to write the function calculate neighbor count. It will return an integer. That is why we have to specify that. And that's done like this. After the function name and parameter list, which is empty here, we add the data type of a return value. tcells has no return value. That is why we can leave that empty here. We just want to print, but calculate neighbor count shall return a value, the neighbor count. That's done by using the return statement. It terminates the function immediately when it's reached this point and returns the given value, which can be a variable or a specific value. So in order to test a little bit, let's just say we are returning 3. So it's very simple and static. It just says for every call there are 3 neighbors. If this works, we should get a true here, alive depending on our initial state, and if it's not alive, we should run here. So a dead cell should become a live cell should stay alive, and this will never happen in our test here. So let's try it, save and run. And you can see that we did some basic thing right, because every cell is now alive. This is our next generation. This is our first generation. As I said, rule 1 or 2 will always apply because we say the neighbor count is 3. Living cells stay alive, dead cells become alive. Now just to check that we got that right, we already covered these 2 branches. Let's also cover this branch. We're going to say it's 4. 4 means that's way too much and all cells become dead or stay dead. Yeah, and that's also working nice. Now we know our basic logic looks decent, and what we need to do next is actually calculate the neighbor count, which is going to be another nice exercise for our previous learnings. Okay, let's start with actually implementing the count neighbors function. We previously implemented the 3 rules of Conways Game of Life, which dictate when a dead cell becomes alive and when a living cell dies. Just to test if we got the rules right, we implemented a static count for the neighbor value, and we saw that our basic logic works. Now let's get to the interesting part of counting the neighbors, because we can learn a lot about how arrays can be processed and how we can handle corner cases. So this is our calculate neighbors count function, right? What we need to have first is access to our playing field, right? So our cells array. Again, remember, arrays are defined by a specific element type and 1 or more dimensions. In our case, there are 2 pairs of brackets, so 2 dimensions, rows and columns. And arrays have a fixed size. They are pretty inflexible with regards to their size. There are also flexible list types in Golang, which are called slices. But this is a topic for another time, one that I'm going to explore in a later video. For now, let's just stick with the fixed array type. Now, remember our sketch. We have a number of rows and columns, and for every given field, we want to count the number of living neighbors. So we're going to start at A1, then B1, C1, and so on, and look at every of the surrounding fields. So when we count the neighbors for B2, we want to look at every field next to it. And when we're right at the edge of the playing field, we have to handle corner cases because there is no left or top or top left field when we refer to A1's neighbors. But let's just start with the basic simple case. Let's imagine we're in the middle of a field like B2, or we have a much larger grid where we are not at the edges. So first we have to know what is our current location. So where do we actually want to start for counting the neighbors? And that's why we need to pass some more parameters. We want to pass the current row and the current column. Both have type int, and this is a shorthand for writing the data type for both parameters. You can write it like this, or if you like the short format better, you can just write the name and add the type at the last parameter with the same type. So you can do it for subsequent types or subsequent parameters who have the same type, but you can't do it if this is something else. So let's say this is a text. Now text is an integer, but actually it would be a string, so I would have to write this. You can't do it when the types are mixed, but in case they're the same, you can keep it nice and short. So now we know what our current position is, and we got the playing field passed as a parameter. So we could look at every individual neighbor cell by addressing its indexes, but let's use loops because they are pretty good for that, and we can deepen our practical knowledge about them by using them. So it's pretty similar to what we already did. But in this case, we're going to start somewhere else. We have to start at a neighbor position, and we have to stop at the right neighbor position. So I'm going to call these variables row start and row end. We increment by 1 in after each iteration, and we do the same for the columns. So again, the compiler is helping us. It's stating that it doesn't know the new variables yet, of course. So let's define them. We're going to use the shorthand declaration and initialization form. And just to define them, I'm going to set them to 0 for now. To get rid of the compile time errors. And now, of course, we also need to count the neighbors. So let's create another variable, neighbor count. And we're going to assume it's 0 for the beginning, and that's our return value, so basically the result of the function. Now, what's our starting and end point for the row and the column? As we can see in our example, we have to start at the top left corner, or top left neighbor, let's say, and end at the top right neighbor. So assuming our current position is this, and when we translate it to indices in an array, this is row 1, column 1. Remember, in Golang, indices start at 0, so this is column 0, and this is row 0. This is column 1, and this is row 1. And the square where both cross each other is our current location. So it's row 1, column 1. And now we need to start at the top left. So we subtract 1 from row 1 and column 1. That's 0, 0. And on the other side, we add 1. We subtract 1 from the row and we add 1 to the column. That's it. So our row start in general is basically the current row minus 1, because we want to go one row up. Row end, on the other hand, is the bottom right. So this is plus 1. Column start is also column minus 1. And column end is column plus 1. So that's a nice symmetry, right? And basically what that means when you combine row start and call start with row end and call end, it says start at 0, 0 and end at 2, 2. So when you look at the loops, we say outer loop iterate our rows. So from one row up until one row down. Start here in this row, then iterate over this, and until inclusive this row. And when you look at the column loop, it's basically the same, just in a vertical fashion. We start here, iterate over column 1 and stop including column 2. So by using this, we're iterating every square once, and we can count the neighbors. So all we have to do is check if there's a living cell at this point. So if cells at row index, column index, and remember we don't have to write anything else because this is already a Boolean, and if statements expect Boolean expressions. We can say if this is true, the cell is alive. So neighbor count can be increased. The long form would look like that, but you know there's a short form for incrementing. It's the same we're doing in our loops. We can write neighbor count plus plus. Now we counted all living neighbors. But remember, we're starting at a specific cell we are looking at, and we want to count all surrounding living cells. We don't want to count the cell itself, so we need to exclude it from our counting. How do we know we're at the center where our reference point is? That's pretty simple, because we know our current row and column. We already used it to calculate the square around it. So we can also check if we're at this position. And how do we do that? We can just add another condition with our logical operators that we learned about. And we want to check that this is not our current position. So row index is not current row. Or col index is not current column. So maybe that's still a little confusing for you if you're not used to these kind of expressions. How do we know we're at the reference point? Well, our current row index needs to be the past current row, and our current col index has to be our past current col. So let me switch it around so it becomes more clear. When you say row index equals current row and col index equals current col, you know this is our position. So that would be the expression to check if we are at the central location, right? So we could write if this is true and then leave this empty. So nothing to do here. And then we could write an else and remove this, right? We could do that. It's possible, but we can do it a little bit shorter. So instead, we're going to say let's do it with a Boolean variable is reference cell and then we can say is ref cell holds true if this is our reference, false if it is not. So we say only check the neighbor count if this is not our ref cell. So you can add a not, negate it with the exclamation mark, and then we need to add a logical end. So count neighbors. This is not our reference cell. Let's say increase neighbor count. This is not our reference cell. And there is a living neighbor. Right, that's probably a bit more clear. You could also inline this condition, or you could rewrite the condition like we did before. You can do some changes that result in the same, but I think you get the point. So now we're counting all living neighbors around us, around our reference point. And we are not including our start point, our reference point. So that's good. Now the only thing that's missing are the edge cases. So for this little example, it's pretty clear that a lot of fields are edge cases, but the same is true for a really large field of thousands of squares, and that's where it has to work too. So how can we detect if they're right at the edge where we can't access all 9 neighbors around it? Well, we have to look at our loop variables. Especially row start row end and call start call end. Because when we are right at the edge, like row 0, column 0, we can't subtract. Then we are in a negative range, and that will trigger an error. You will get a runtime error and the program will crash. You know, just to illustrate it, we should just try it, right? I mean, testing is a good thing. So let's run our function. You're going to see a crash. But first we need to make the compiler happy, and it complains that we are not passing the required parameters. We need to pass cells and our current position, which is row index, col index, as you can see from the loop. So of course cells is unknown. We have to give a valid variable name, and this is first cells in our case. So save, go to the terminal, type go run main.go, and that's our crash. It says panic, runtime error, index out of range, -1. So from the error, it's pretty clear what the issue is. And the nice thing is when you look at it, there's a stack trace that tells you exactly where the error happened. It's in our main.go file at line 48. So this is it. In this line is the error, and it says index out of range -1. So -1 is out of range because arrays and also other list structures are indexed from 0 to the size of the structure -1. So obviously negative indexes will not work. That's a typical mistake and error in pretty much every programming language. It can happen anywhere if you are not careful. And when you look at the stack trace, it tells you the call chain. So not only can we see the line where the error happened, we can also see where the function was called from. So line 13 is the location where our call is. Now for our little program, it's not that important. But when you have a large code base of thousands or even millions of lines, this is pretty nice to know because there's a lot going on and you don't necessarily know where the function was called from. And then you get a whole stack of locations and you can look through your program where it happened. Now that we see the crash, let's do something about it. We need to restrict the indexes somehow. I mean, you can see that we're out of range when we are in the negative integer space. And on the other side of the array, we are out of range when we're larger than the size -1. So the size is 3 times 3 in this example. And this is index 2, 0, 1, 2, right? So the max valid index is size -1. 3 minus 1 is 2. So when the index becomes negative, smaller than 0, or becomes the size of the length, or even greater, we are out of range. That's what we have to take care of. So for row start, we can say if row start smaller than 0, we have to limit it to the minimal value that is still in range, and that is 0. Right? The same in the other direction is true for row end. If row end is larger or equal to the length of cells, so 3 in our case, but we're going to write it using length because then we can change the size later to a much larger field and it will still work. Then we need to restrict it to the max valid index, and that is actually the length -1. And now we need to do the same for the columns. -1 is the last valid index. Now, one thing to mention here is for row end, we can just take length of cells. So this will give us the length of the outer array, the number of rows. For columns, we should rather have a look at the length of the inner array. So I give it cells from 0, meaning the first inner array, which is the first column. So it looks at the number of columns. This is important just in case the number of columns is different from the number of rows. Imagine we would have 3 rows and 4 columns. Then it would be wrong to stop at 3. So remember that when you're handling two-dimensional structures like this. Now we got our restrictions in place. And we can start our program, save. Let's see if we did a mistake. No, we didn't. It works. But let's check the rules just to be sure. We can just compare it with our example. Yeah, that looks nice. This is our first generation. This is the next one. Yeah, it looks good. To make sure it works, let's start with a first generation of this pattern. So it's false, true, false, true. Then 3 times false. True and false again. And we should see our expected pattern. These 2 living cells, the rest is dead in the next generation. And that looks fine. That looks like we did it right. So nice. This is the neighbor counting. Now that the neighbor count works in general, we can have a look at how to clean up the code a little and improve upon what we already have. This is a typical thing that's done in software engineering and programming in general. You break a problem down into a smaller set of tasks and you solve each small task for itself because it's much more manageable this way. And once you have a small task achieved or even a bigger one, you can go back, reflect a little and look at the code. Always remember that you are going to look at the code in a few days, weeks, or even years. And typically you're working in a team where also other people are going to look at it. It doesn't matter if it's a large open source project that is developed basically on the internet, or if it's a company where you're sitting together in an office. It's either you or somebody else who has to read, adapt, and maintain your code in the future. So please do that human being a favor and keep your code as clean and readable as possible. And one thing I'm seeing here is that this is pretty much quite some repetition and a little bit of unnecessary complexity. What we basically do here is we are restricting our start and end point to a minimum or maximum allowed value, so we stay in range, right? So we can just write a little helper function, min, and a function max that does it for us. So let's write a function min that takes two integers, and let's call them left and right, and it returns an integer, specifically the smaller one. So if left smaller than right, return left, else return right. It's very similar for max, just that we're writing if left bigger than right, return left, else return right. Now you might be wondering what happens when both are equal. Well, it doesn't really matter which one we return, then both are equal, right? So in this case it's going to be right. Now one thing you can see here is that we use an if-else, which is perfectly fine. You can write it like this. But one thing some programmers and also me like to do is you can shorten it a bit by removing the else clause. Why can we do that? Well, return immediately exits the function. So once a return is reached in a function, it immediately exits. And when there's a return value, it exits with the return value. So if this is true, we go inside here, return left, and the function is exited. We're back to our calling point. So when I'm calling it here, min1, 2, it says, yes, left is smaller than right. That's true. Returns left, which is 1. And we are back to this line, and program execution continues below. So that is why you can shorten that. In case it is not true, the next instruction is the one below, and we know that there's nothing else that is relevant there. We know if we didn't run here, right is equal or greater, so we can immediately write return right. And the same is true here. So now let's use our neat little functions and translate it. We can now write row start is current row minus 1. That's the happy case when we're not at the edge. But we say our min value, it has to be at least 0. So we did create some new code here. Due to the extraction to a function, this code becomes much cleaner, and the nice thing about it is we can reuse the code without repeating ourselves. So we can use the exact same function call here. And for row end, you already guessed it, we got max. It's the other way around. Current row plus 1 is the happy case. We are not at the edge column, edge row in this case. But we say it's at least length of cells. No, sorry, it's not at least. It's no greater than length of cells minus 1. So the last highest valid index. For identical, and it's the same with the column. Again, remember we should take the column array, that is the inner array of the two-dimensional array, and that's it. Let's remove the white spaces so we got a nice and clean setup of our variables. And now to see if we got things right, let's test it. Oh, there's a crash. Nice. Now we can figure out where it happens. It says index out of range, so I did a mistake somewhere. And it crashes at line 62. So again, when accessing the cells, let's see where the error is. Can you see it? Yeah, we got the order of the function calls wrong. You see, we're starting at the top or the left, right? So we want that the smallest legal value is 0. And when we're in the negative range, the higher value needs to win. So it's the other way around. We need to use max for the out of range to the negative side, because 0 is greater than a negative integer. And we need to use min for the right side where we are beyond the, at the size bound or beyond the size bound of the array. So let's test it. And yeah, we fixed it. It looks like before. This is what you call a refactoring. We kept the functionality, at least now that we tested that it still works. But we improved upon the code. So we made the technical side better without changing the functionality that you can see from the outside. So that was a little refactoring exercise. I guess now our function looks pretty clean. The next thing we are going to do is we are going to extend our program to actually run through multiple generations. So up until now it's pretty boring because we only got the first and the second generation. So this is what we're going to do. We're going to keep it running. And we also want to increase the size of the field so it becomes more interesting. So at first, let's try with the increased size. Let's say we want to use 30 times 30. Now what we need to do is we need to change the size dimensions everywhere the cells array is specified as a variable or parameter, because these are two different types. You can't use a much larger field, 30 rows, 30 columns, at a place where a much smaller field is expected. So that's the compiler that checks the type safety and tells you you can't do that, that's a mistake. So that's pretty useful. But it's also a little of a hassle because we have to, every time we change the size of our playing field, and we want to do that easily, we have to do it at each and every location, which can become quite cumbersome if we have a much larger program. So luckily for us, there's a nice feature in Go that allows us to simplify it. And it's called a type definition. What we can say is we can give this type that we declared here, we can give it an alternative name. And then we can use that name everywhere where the declaration is used. Let me show you how it looks like. Right at the top, that's usually a good location to not miss it during reading, we can write type, and now we give it a name. Because it's our field of cells, let's call it cells. And now we have to say what is behind this type, and of course it's our Boolean array. And that's it. Now cells is an alternative name for the compiler that stands for a two-dimensional array of Boolean fields with 3 rows and 3 columns. So now we can use that type name everywhere in place of the old declaration, which is pretty nice. And as you can see, it's really just an alternative name, because here at our function parameters, it's still the old declaration, the old format. Here it's a new type name, and the compiler's not complaining. We can run our program, it still works because it's just an alternative name. But of course it's much more comfortable and maintainable if we use it consistently. So let's use it here and here. Let's see if I missed something. No, that's everything. Okay. So now to check that, the nice thing is when we change the size of the field, we only have to do it in one place. So now we say 4040 and that's it. I don't have to change anything else. And that's it. We got 40 rows and 40 columns. And as you can see, we did a good job of using loops and variables. We didn't hard code any indexes, and that's why it still works with a much larger field. Now, 40 rows might be a bit too much, and 40 columns is a little bit below what we can do. Let's say we use let's say we use 20 rows and 80 columns instead and see how that looks. Yeah, that's pretty good for my screen. And now we can work at building new generations. But before we do that, let's change the way that we are initializing our first generation of cells. For a large field, it's pretty tiresome to enter the starting cells manually. So what about we start with the random set of living cells. We place them kind of like in the middle, and we add some randomness. So every time we start the game, we start with a different generation and get different patterns of living and dying cells. Now, how do we do that? Well, luckily for us, there's already a function on the package in Go for generating random numbers. And that's what we're going to do next. When you want to check if there's a standard function for Golang, you can just Google it or go to the languages web page and search the docs or packages. And we're going to search for random. And we already see there are some packages like rand mathrand or cryptorand. And you can see these are standard libraries. They are tagged as such. It does also search with the internet for other sources like GitHub, golang.org/x, which are some kind of helper libraries, and so on. But usually it's a good starting point to check the standard library, and if that's not sufficient for you, then look for other libraries that might already exist. Of course, it's always helpful to look at the license. If it's a free and open source license, in this case it is, so we don't have to worry about any licensing issues. Now, you might be asking, shall we use mathrand or cryptorand? Well, cryptorand is more for cryptographically secure random numbers, like it's described here. So if we did something about keeping messages safe and secret, then we would use such a library because they have special requirements for safety. But for other reasons, we can simply use this math package where there are random functions. Now we can browse the documentation and look, okay, what functions do we got here? So we don't have to implement them ourselves. There's an index. What we want is we want random integers. That's what we're interested in. So a simple int type is okay for us. So let's check this function. And it says returns a non-negative sort of random int from the default source, which is nice. The only thing that's missing it is we can't say in which range this random number should be. So we look further through the functions and we see there's int n. And it says returns an int, non-negative random number from 0 to n-1, so n excluding from the default source. I guess that's fine for us. There are even examples that you can try, and it shows you how to use it. So random from 0 to 99 3 times gives us 3 different numbers. And there's also an explanation that you should set a seed. That's basically the initial value for generating these random numbers. You can think of them as a starting point. So it's a good idea to use the current time as a starting point because it constantly changes. We want to have different starting points each time we are running it, because when you use the same seed over and over again, it will result in the same sequence of random values. That's just because of the way these pseudo random numbers are designed and implemented. So we can even copy a little bit and say we need to import the package mathrand. Remember, for every function that is not in our own source code or our own module, we need to import it. And once you have multiple imports, you can simplify it a little and list them inside parentheses, so you don't have to repeat the import statement time and time again. Now let's see what it says. Could not import. Okay. So it seems we did something wrong. FMT still works. And math rand works too, but it says it's not used. Okay, so that's the issue. We have to use it, otherwise it's an unused import. That's the complaint from the compiler. So let's make sure we are using it, and at the beginning we're just going to copy that to check that it actually works. Yep, that's it. And as you can see, although these are random, they repeat at the second run because we use the same seed, right? So what we want to do is we want to have some randomness in there. And I believe we can use the time package for that. So time dot is a time time.now.unix nano is what they recommend. So time.now gives us current time, which is it's a delta value from 1970, from the 1st January. If you're interested in that, just Google it and you can read about how this is implemented in Unix. But for us, it's sufficient to know that this changes with every passing nanosecond. So now we will get different values, right? 91, 55, 82, 17, 61, 6. Nice. So this works. Now we got our random numbers. How do we use it to actually generate starting cells? Well, we said we want to populate the initial cells in the middle of the field, so they are not right at the edge and have some space to grow. Let's write a function that we call generate first generation. Or let's just call it first generation. I think that's precise enough. It's returning a two-dimensional array, but we're going to use our neat little type cells. And we can copy our random code here. Now, again, we need a loop because we want to populate an inner region. So just going to copy our usual looping code here. And as you can see, we need to think of the dimensions. And the actual length is, yeah, basically defined by our size. So we create our initial field that is just a declaration for us. So cells cell, and we're not initializing it because we do that in the loop by default. Boolean values, Boolean fields are false. That's pretty useful for us because we can assume that everything we didn't populate with a living cell is dead. So now we can use the length of cells to iterate the inner array cells from row index. Now the difference is, to all the other loops, we don't want to iterate over the complete area, but just in the middle. So where do we want to start? We could start at the middle, right? And then draw some kind of square around it. So let's say we start at half of the length of rows, half rows, minus 5. And row end, there was a colon missing. Row end is, oh, we didn't have it, divided by 2, that's the division operator. We need to put this in parentheses, as you probably know from calculating numbers, in order to give precedence. So, and this is length of cells divided by 2 plus 5. So from the middle, 5 to the left, 5 to the right. And actually we don't need the parentheses because the binding is stronger. And we will see how it works out. Call start, call end. Now we have to take care to use the actual column length, so inner array, and we can just use the first one because it's always a square. Rectangle, I mean, sorry, it's a rectangle, not a square. Okay, now it's still complaining, but just because we're not using them. But we're going to change that. The end is exclusive, so length is no longer required here. So we are including row and -1 and column and -1, but not the end itself, like we did for neighbor counting. That's why we used smaller or equals when calculating the neighbors. Okay, now we got an inner rectangle. Since we have more squares in horizontal space, let's double that, I guess. We could even increase it, but let's say we double it and we say column -10, column +10. Just to make sure we got that part right. We don't want to code too long without getting any feedback, because then it's getting harder to debug and fix mistakes. We're just going to draw a new character there so we can check if it works. We are going, no, not print. Printing is already implemented. We say cells from row index, col index. We can say this is a living cell just for now. Big O. And the rest will be dead, so we're going to recognize it. And now we are still missing a return value because we said we would return cells. So we need the end return cells. That's it. So now we still need to call it because the function is not used. We no longer need our ugly by hand initialization. We have our fancy function for that. And then we print first cells and next cells. And yeah, that's it. I guess because the inner area will be populated with a huge amount of living cells, they will mostly die in the next generation because they have too many neighbors. But let's see if we got that right. Undefined cell, okay. Undeclared name, yeah, because the type is cells, because there are multiple. And that of course is wrong because it's not an array of strings, it's an array of booleans. And of course living is stored as true, so the compiler is there to the rescue. And during printing it's translated to an O. So that's it. As you can see, the inner area is populated with living cells in the first generation. And as we said, due to overpopulation, only the outer space, as you might say, survives because there's more room to breathe and there are not so many neighbors. Yeah. Actually, it's a little bit hard to recognize the difference, right, between living and dead cells. Maybe we can use how about we could use a blank. Yeah, let's try a blank for dead cell instead. Go to our print function. Let's see if that looks good. Yeah, that's much nicer to look at. Now maybe we need some kind of separator to see where the next generation starts, or maybe we can use a dot, just dot. Yeah, I guess that's a decent way of seeing the field and the cells. Now, let's get to our random part. This is completely static again, in order to have a first feedback loop for testing. How do we use the random part? Well, you can interpret our random function as a dice roll or as a probability, and we will use that to our advantage. So rand is a package, and int n was the function we looked up in the documentation. Now, let's say we want the chance of a cell appearing to be 1 in 4, so 25%. That means when we pass 4, we get 0, 1, 2, or 3. Each has about the same chance, so 25%, to get one specific value of 0, 1, 2, or 3. Let's just use the 0 and say if this random value is equal to 0, remember the double equal sign, because the other single equal sign is an assignment, not a comparison, then we spawn a living cell. Otherwise, we don't need to do anything because the default is already false. You could write else cells assign false, but it's not needed, so we keep it short. And since this may be a little cryptic to a new reader or to ourselves in a few days, we write a little comment and say there's a 25% chance of a living cell spawning. Let's see if this works. Yeah, run it again, and you can see when you run it repeatedly, it gets nice and randomly. It's never exactly the same. It looks kind of random, and that's what we want because it gives our game the option to be not predictable. And once we create generation after generation, we get nice new patterns every time. So the next thing we're going to do is do exactly that, generate repeated generations, so I don't have to start the program that often, and we want to see more nice patterns. Okay, now our program is already pretty solid from a functionality perspective, but of course we want to add some more things. At first we want to make sure that multiple generations are generated automatically. So we already saw that we are only generating the first 2 generations. And afterwards we're going to improve the visualization part so that it looks a little bit more nicely and not so simplistic, although I kind of like the current display for development purposes and just to see if we got things right so far. So let's get back to the code and make sure we're continuously updating the playing field. So we already got 2 loops iterating our array of cells, rows and columns. And in order to do that repeatedly, you guessed it, we have to use another loop. So first, before we get too messy here in this function, because we want to avoid too much deep nesting for readability reasons, we should extract some code. So basically do a refactoring. So let's think about what we're doing here and how we can extract it. We're iterating the field and we're determining the next generation. So our first generation is created by this function call, and everything we're doing here is determining the next generation of cells. So it's just a good idea to extract a function which is called next generation. It's returning our cells type, which is just a two-dimensional array we defined above with the type directive. And then we are cutting and pasting our code from above. Of course, we need the variable for the next generation. And we need a return statement. Otherwise, the compiler is going to complain about us. And in order to calculate the next generation, of course, we have to look at the old generation. So we're not only returning cells, we're also passing them. So cells is our parameter. And now we have to rename this variable because it's no longer the first cells variable. Remember, we are going to call it repeatedly. So let's just call it cells. Could also call it old cells or whatever, current cells, something like that. Now, in terms of printing, we are just going to use one variable in our main function called cells, which holds the current generation. And let's just remove the printing for now. We're going to re-add it later. Now, of course, we need to call next generation past the current generation in order to get the next one. And you can see we can do that by calling the function next generation and passing our variable. Now, the interesting part is we can also use the same variable for storing the result. That's not a mistake, that's pretty normal, because the function call happens first and the old state is passed. When the function call is done, we no longer need access to the old state, right? Because we already determined the new state of the cells. So we can reuse that variable to assign the new state. And now, of course, we still need our loop. You might be wondering what does our loop consist of? What about the initialization part I explained about, and the check condition for every iteration, and the update after each iteration, like in this case? Well, actually, you don't have to specify every single part of it. So most of the time you will do that. You will need an initialization part, like a row counter. You will need a condition for exiting the loop to know when you're done looping. And you will need an update, like incrementing the row counter. But the language doesn't force you to do so. In some cases, it can be useful to omit one or multiple of these parts. We could write an endless loop like this. It means all instructions inside here will be run again and again and again. There's no exit here. Usually that's a bad idea or a mistake. Sometimes, especially beginners, make the mistake of accidentally having no valid exit condition, and the program gets stuck and you have to terminate it. Actually, let's just demonstrate it. I'm going to print a test message here and save, run. And you can see it's printing and printing and printing, and I can't do anything. I just can press Control C to abort the program. That's the only option I have, killing or aborting the program. So usually you don't want that, but sometimes it can be useful. We could leave it like that and yeah, just terminate our program. Usually you will want to add some kind of input querying, so when the user is pressing some kind of key that you can exit the program gracefully. What we're going to do is we will use a counter again, and we are going to calculate, let's say 20 generations. So count 0, and from 0 to 19 we're going to print new generations. And now we still need the printing. We already got our function print cells. We can use the same here. So actually these are 21 generations because the first one is outside of the loop. We have to do that because we need to call first generation, which is different from next generation since we are using some random initialization part we programmed before. But that's fine. Let's just use one initial step and 20 next generations. Now let's try this and see what happens. Oh, it actually works. And you can see there are interesting evolving patterns. But it actually happens very fast, right? Because the machine is much faster than our eyes. So let's add a little delay in there so we can actually see the movements. We're going to use a standard function for that. And again, you can use the internet to your advantage. And there's this package search function where you can search for functions. Let's look for time. And you can see this is the standard library. And it has something like clocks and current time determination. And what we actually want is a sleep function. It's commonly called sleep in programming. It pauses the current Go routine. That's a topic for another time, but let's just say in our case it's the program for at least the duration d. So an example would be time.sleep 100 times time milliseconds. So let's just copy that. And we're going to add a delay here after the first generation and after each next generation. Or even better, we can avoid one of these, simplify our code, and instead sleep at the beginning of the next generation. So we got the delay even after the first generation. Now we already got the time import, so that import is already there. But 100 milliseconds is a little short for our eyes. Let's say we use 1 second, and we don't even need the multiplier because it's 1 by default. We can just say sleep 1 second. Now let's see how that looks like. Yeah, now we got some kind of evolving playing field. And you can already see that's a good speed for our eyes where we can actually realize the changes. And there are some patterns that were static or moved in the same pattern. Like these blocks are static and these are some kind of rotators that change from vertically to horizontally. So that's already pretty nice to look at. And yeah, so we pretty much covered our functionality from a evolving cells point of view. Now, the only thing that I wanted to include in this little tutorial is to use another third-party library and improve the displaying. I already showed you in the beginning that I got some colors and that actually let's run it. Now let me show you that later when we build it. You got one playing field in our improved simulation, and this is just printing one after the other, right? But it would be much nicer to have one evolving field, and that's not so easy when you program it yourself in the terminal. Luckily for us, there are many third-party libraries out there for all kinds of programming languages. Of course, that's also the case for Golang. And on GitHub, I found this interesting project that is basically a package where you can have nice displaying in your terminal. So you can easily address certain locations, certain areas of your terminal output and render them. So it's not like we are printing one after the other, but we're actually addressing specific locations on the terminal like we do in our array. And the library handles the rendering for us. We can also use colors and draw things and all kind of stuff. So first I identified this interesting looking library. We can see it's an open source license, so we can use it pretty freely. And there is some documentation and a tutorial that we can use to get to know how to use it. So that's pretty much always a good starting point to look into the documentation or maybe some examples for understanding how to use it. So let's start with a very simple example. You can just copy this and we're going to deactivate our code for a minute to focus on the new library. For that I'm using multi-line comments. So these are single line comments that are just for human beings and ignored by the compiler. And you can use multi-line comments in the C language style using asterisks and slashes. So basically I made that a comment and it's ignored by the compiler now, but we didn't lose it, so we can quickly remove the comment markers and re-enable it once we want to. So now I'm copying the example code and we just want to get started with the library. So it's called tcell. It's actually located at GitHub, gdaemon tcell. So this is what we are going to use in our import function. Yeah, it looks like this. We need to import it. Now it says could not import, could not find package. Why is that? It's because it's a third-party module. It's not part of the Go distribution. So these are standard libraries. These are included in your Go installation. This is a third-party library. Not everyone needs it like a standard library. So we have to download it from the internet in order to use it. That's actually not that difficult. We will use the Go module system for that. It's pretty simple for our use case. Now go back to your terminal and to your project folder where your Go file is. And we're going to call Go mod for module init. And now we need to give our program a module name. You can use what you want. You can call it example or game of life or whatever. I'm going to name it like my subpath, because that's just a kind of good practice if you want to later publish it, maybe to GitHub or something like that. So it's telling us that it did. It created a new Go mod file for our module name. And in order to add modules, we can run go mod tidy. So what is it actually about? This is about managing dependencies. So in a real software project, you usually need third-party libraries. Programmers don't reinvent the wheel every time they write a new program. They use what is already available. Not only the standard library function, but also external libraries like the one we want to use now. And somewhere in your program you have to define what kind of libraries you need. It's like a list you make for cooking. You need ingredients to cook a certain meal. So you have a recipe where all your ingredients are listed. And that's kind of the idea of dependency management. So our Go mod tool created a new Go mod file, and that is basically our recipe file of dependencies that we need. Right now there's not much in here. It's the module name from our module and the Go version that was used. But once we run go mod tidy, it will detect our import statement and find out that we actually need this dependency. And it's looking for the module, found it, and added it in its current version. So now when we look at the file again, we can see there's a new line require, and that is because we require this dependency, this external module. Then there are also some indirect requirements. This is because there's some kind of chain reaction. The people who created this library, of course, they also used some libraries to get the work done faster. And that is why there are some indirect dependencies that are required for this dependency. So although it sounds quite complex, the basic idea is pretty simple. Now that we got our recipe and Go knows which libraries we need, we can use it. The error disappeared and we can now use the code and the functionality that these friendly people already provided. So back to our minimal example. The module tcell, we create a new screen in the terminal by using new screen. It returns a screen. I'm going to name it screen instead of s, so it's a little more descriptive. And as you can see here, functions can return multiple return values. This is such a function. And one common use case for this is to be able to check for errors. If something goes wrong, you want to be able to detect that something went wrong and handle the error instead of crashing the program. Most of the time at least. So this is when you check if everything went fine. Nil is a special placeholder value that stands for nothing or not set. It's known as null or none in other programming languages. In Golang it's nil. And in this case, checking error for not nil means if there's an error, this will not be nil, it will be an actual error. Then we have to exit the program or we have to handle the error. This is done with this log fatal F call. Log is basically a way of printing information, debugging information, and it's pretty similar to printing to the terminal. It's just a little bit more flexible about how it's done, where it's logged, and in which format. So this is just error handling. If something went wrong, we say terminate the program and print the error. The same happens here where the screen is initialized. Just some setup. Next, style is set. So we're already seeing it can set a background color and a foreground color. Both are reset. So back to the default color. And the style is defined first, then it's actually applied. And then the screen is cleared. We are still missing some key function calls for actually seeing something in the terminal. So let's go back to the documentation. And the minimal code that we saw here is just the setup code. And then there's some drawing going on. Like this code is going to write the word hi to the terminal. And you can see here that it's positioned by using indexes again. Now one important thing here is to note that the order is a little different. When we're referring to the screen with this tool, at first we are specifying the x coordinate, which is basically horizontal, so column as you might say. And the other one is the row coordinate. So we have to switch it up when we think about our two-dimensional array structure and the screen indexes. So let's give this a try to actually have something drawn to our terminal. And there's still something that we're missing because we just cleared the screen and set the default style. We also need to show our drawing. And that's basically screen.show, update screen. We could also do event polling. That's for when the user enters certain keys or mouse events, but let's just start very simply. Now we update the screen. And for our program to not get stuck, I guess we should also exit in a clean way. Let's look at this demo application, and it's having some utility functions for drawing. Then it's the main code, two styles, initialization. We don't need the mouse yet, clear, some drawing, and then there's the event loop. We can talk about the event loop later. Let's just make sure we have the show, and we got the quit call at the end. That's screen finish and OS exit. We can skip the OS exit because we don't have a loop yet that we need to exit from. So finish terminal program. Now we need a style for the drawing because our default style says use the default terminal colors. And actually this could be enough. Let's try it to actually see something. No, and it did immediately exit. I guess since we don't have a loop yet, we should add a small sleep like we did before. Let's say 5 seconds should be enough. And now we can see we get a fresh screen. It's no longer the scrolling terminal we had. And it's actually rendering. So we get to write our letters in the first row of the rendered screen. And then after 5 seconds it exits. And the nice thing about it is you can write more complex terminal applications now. You're not restricted to printing one page after the other. You can actually quite dynamically render something. We could start drawing some lines, like when you want to program a little game. So let's say we want to draw a line from 0, 10 places long. It's just one of our usual for loops. And then we say set content, and we want to draw a line in the third row. So remember, that's the second argument. And this is our index, so the column of this row. Okay, I missed the colon. Now it's correct. Maybe you already spotted that because index needs to be declared. This is an assignment, and I can only assign after a declaration is present. by using colon and the assignment operator, I combine declaration and initial value. Now we need a style. Let's call it our draw style. And we define it up here. We say draw style has a background of light green and a foreground too. It basically doesn't matter because we want to fill the whole cell with a solid color. So it doesn't really matter which character we type here. We can just use a space, blank, and background and foreground will ensure that there's a green line. So we pass our draw style, and Neil just says don't use any real argument here. You can pass a slice of runes. I don't want to dive too deep in here, but you can read the documentation, and it says that usually the array that follows is a possible list of combining characters to append, and will usually be nil, no combining characters. So you can just remember that we don't need it for our purposes. So we just leave it empty, therefore nil, the none value. So let's try this. And there you go, you got this line. Now we could do all kinds of fancy stuff with it. We could start writing a snake game, or maybe draw some pictures, just create a user interface for an application where you can serve input and output. Lots of things. But let's get back to our original purpose, to visualize our cells from Conways Game of Life. So now we need to adapt this library usage for rendering to our actual data, to our generation of cells that we programmed. How do we do it? Well, what we are still missing is an event loop, like the documentation shows us. We're just going to copy one of these loops, and don't get too confused about it yet. Most of the code we don't need and can remove it soon, but we will check it line by line. So the event loop is basically for interactive programs, games, etc., where the program is running until the user closes it, and we are constantly checking for input by the user. So, of course, the most important thing is to have a loop, and that's our for statement here. And on each iteration we want to update the screen, right? So that's why screen.show is here. We also need that. Poll event is also interesting because it allows us to check if the user entered some key. If he pressed a key on his keyboard, or if you enable mouse actions, we can also check if the user did some mouse action. The event is then processed. So just checked here what it is. That's a switch case statement. You can basically think of it like a large if-else cascade. We could write it with if-else, But switch case is basically an alternative form that allows you to handle certain state based off one variable. In this case, it's event. It's the type of the event. And then the case statements say what shall happen in each case. So events can be of different types. There could be a resize event. There could be an event key, so the user pressed some key, or a mouse event. Let's remove the mouse event to have this a little bit more cleanly. We don't need it. And let's have a look at the rest. So what is happening here? This is actually the type of the event. So it's basically a type check. So I guess we're going to handle these kind of things in a later video. I don't want to confuse you with too detailed concepts of programming yet. But you can just remember that this is a check of the actual event type. And this fancy asterisk here means that this is actually a pointer. Pointers are parts of the data type, and as the name says, they point to specific values in memory. About the purpose of pointers and how you use them, we can talk in another video because it's a topic in and of itself. So just assume that this is how you use the library here. A resize event means that the size of the terminal changed. So for example, when I go here and I make it larger or smaller, then we may have to react to that, and that's why you can capture the resize event. It calls screen.sync, which is similar to show, but it's less optimized. It synchronizes the complete data that we have for showing to the screen. Basically means re-render the complete terminal screen, because in a resize requires that usually. Show, on the other hand, is smart. A show determines what actually changed when we used set content, and it just updates the places that actually changed, so it's more efficient and usually preferable. Finally, there's also the event key, event type. That's when you want to check for certain keys that the user pressed. Hang on, okay, there was a missing closing brace. You can see them in most editors. When you mark the opening or closing brace, you see the other one around, and due to the missing brace, the compiler got a little confused and didn't even detect here the mistakes that are still present. So what key events do we have to handle? We should handle the escape key and Control-C, which usually means abort the program, stop the program. So that's what we're going to handle. For now we will not use the other ones, so just keep it clean and nice. Quit is actually a function, and we're going to replace it with the implementation, which is finish, and then os.exit, which means terminate the program. And we pass 0 because it's a return code which indicates program terminated without errors. You can pass different values, and that's a convention, e.g. on Linux, to indicate an error. Now let's see if our event loop works as expected. We're going to put the drawing inside the loop. When we're repeatedly drawing, and the sleep at the beginning, but we don't need that much sleep, let's say 100 milliseconds, so we're not drawing as fast as we can, but with small breaks in between. After all, we're not going to change the rendered output anyway now. So this is it. Let's try it. Okay. And now we can see it's rendering in our event loop until I'm pressing escape or Control C like I did now. Now that we have some basic output using this rendering library, tcell, we can actually start adapting the library usage to our data and to our Conways Game of Life. So what do we need to do? We need to take our cells where we are calculating the generations, and we need to translate our living and dead cell array to the elements that we render to the screen. So it's actually not that difficult. We start by re-adding our cells. I'm just going to cut it and move it here. But we no longer want to print the cells using our standard output functions, so we can remove it. And we can also remove our original loop and the sleep, because we're going to integrate our next generation calls into the existing loop. So obviously we need the initial generation at the start. That's what we're doing here. And now we need to update to the next generation inside the loop. So after the small waiting period, so it doesn't run too fast and we can actually see things with our eyes, we add the function call for the next generation and reassign our cells array. Now the data is integrated into the start and the loop, but we are still missing the actual drawing of our cells. So what we need is a new function. Let's call it draw cells. And we're going to pass cells and write that function. What we're also going to pass is the draw style, because it allows us to change the color of the cells. Just appear and pass it to the function, and the function can handle the set content calls on the screen. And as you might guess that we also need the screen for calling set content in order to actually draw something. So let's write the function down here. Cells is our own defined type. Then there is a screen, which is of type screen, tcell.screen. You can see that here. And then there's the style, which is tcell.style type. And we're just going to call it style. That's it. We don't need to return anything. We just want to call set content on the screen for our living cells. And that's why we don't need a type here at the end of the function header. We are also going to call clear after every iteration. And clear resets the screen, as we read in the documentation, to the default style that we set here on the screen. So that means we don't have to handle dead cells. We just need to draw living cells, so where our elements in the array are true. So it's the usual nested for loop. Again, take care of the length. In an array, so cells of row index. And now we just have to take care about the dimensions. So let's assume that we have enough space for our rather small data grid. But we also have to consider the inverted indexing. So while our two-dimensional array is indexed by row column, the screen is indexed the other way around when you read the documentation. So it's X first, which is in this case the horizontal index, and the second index is the vertical. So we need to change it around and pass the column index first, then the row index. Yeah. Then there's the style. And as we saw earlier, set content, sorry, set content. By the way, what is set cell? Older API and will be removed. Okay. I was just a little confused because set cell sounded so right. Maybe because we're talking about cells all the time. But actually it's saying it's deprecated. Please use set content. So X, Y. The rune is basically a character. This is this fancy feature that we're not going to use, and then style. So we're just going to use blank again, because our style is going to fill the location, and nil for this feature that we don't need yet. So, but we're not going to do it for every cell, but only if there is a living cell. So again, we have to check the Boolean element here, and here you can see it's row first, then column. Otherwise you get a nice twist or an out of range error. So let's see how that looks like. Draw cells is called, we call screen show. Next iteration is going to sleep shortly, so our eyes can see the difference and calculate the next generation. We're still missing the clear call, so that's, and we need to draw the first generation, so let's call draw cells here and pass it to, that's for the first generation, screen draw style. And then we need to clear the screen, draw the new cells, show the new screen after we calculated the next generation. Now one more thing about event polling. We need to check events in order to detect resizes and when the user wants to terminate the program. But poll event is going to block until there is actually an event. So if we leave it like that, we are going to see the first generation, the second one, and then nothing more is going to happen. Let's try it. Yeah, so that's it. It's not changing, and that's because we're inside the loop and the program is waiting here. It's waiting for us to give it an event. So if I do a resize, you see it did another iteration. So it's waiting for an event, and once an event comes, it's continuing. But that's not what we want actually. We want to handle events only when they are present, and if there is no event, we want to continue rendering. Luckily, there are different functions in this library that allow us to do this, and we can query has pending event. You can see it's a function returning a Boolean. So it's very simple. We can say if screen has pending event, process the event. And we can move the distinction of the event type inside the loop, inside the if branch, sorry. And obviously, if there's no new event, we're just going to continue with the next iteration of the loop. What we still need is to get the event, so we can still use poll event for that, but this time we're just calling it if there actually is an event, and we're not blocking the program if there is none. So let's try this. And you can see now we got our continuously running program, and these cells evolve until they are no longer moving and pretty static. Yeah, and that's it. For our small example, it's not going to evolve anymore. Now we can press escape or Control C. And again, and due to our randomness, we will get another evolving life of cells. So this actually evolved differently. It was, I think, much longer that something was going on, and now it's completely static, no rotating, nothing more. And the nice thing is we can now make little changes to our program without much, have an impact without much work. So I can say, okay, let's increase the size. We're going to use 40 rows and 160 columns. And we can say background shall be different. What is a nice background? Let's say, I think I used light green as a background on my original implementation and purple as the foreground. Of course, you can experiment with that and see how it looks like. Okay, there's did a typo there. Purple. Yeah, it's a little intense. Let's say maybe violet, dark violet, and yeah, much better. So now we got a larger field, and yeah, you can see it's evolving quite nicely. And there's not much more going on. Still something going on. Now we could do all kind of stuff like maybe we want to slow down the size to 1 second so you can have more time looking at the evolving cells, but I guess much more interesting is to speed it up to, let's say, 10 milliseconds, and then it will evolve much faster. Oh, it's already done. Oh, that's pretty fast. Maybe a little too fast for watching. So something between 10 and 100, let's say 50 milliseconds could be nice. Yeah. Oh, that's a nice pattern. Oh, quite a lot. Yeah, so now one thing that we can do at the end is to revisit our program and look how we can clean it up a little. This is already pretty nested here. Could create a function for setting up the screen. So let's call it init screen. and it's just responsible for creating the screen, doing the error handling here, and setting the default style. So we're going to move this to our init screen function and then return the screen from it. Of course it's tcell.screen because it's an external package. Let's move the function at the bottom, and then we can call it like this: screen, declare and assign init screen. Looks a little bit cleaner now. And now for the loop. It is basically when rendering what we're doing here. We could extract the event handling. Yeah, I guess that's a good idea. Let's call the function handle event. And it needs the screen again. tcell.screen doesn't need to return anything. We can move the handling inside here. And then we just call handle event pass the screen. Now our main function is much easier to read. You can immediately grasp the basics. Like there's a screen that's initialized, then we build the first generation and draw it. And the main component is the event loop, which calculates and displays next generations. And there's a handle event call if there is any event. So this is already pretty easy to read, right? Now as a final check, let's see if it still works. We actually wrote about 200 lines of code. It's not that bad for a little tutorial. And let's run it one more time. And you can see it still works nicely. Oh, there's even, that's an interesting ending. I didn't see an ending like this before where actually 0 cells were present at the end of the cycle. Now, I hope you enjoyed this. If you get any questions, let me know. I highly recommend to program this yourself if you didn't do it along the video. You can always go back and watch certain parts. You can Google around if you don't understand something. There's a lot of material out there also for beginners and for people who want to learn the language. Just give it a try, and remember, you are only going to really learn things if you put them into practice. So just watching or reading alone is not enough. You have to put the theoretical knowledge into praxis. If you already got this program, or maybe you want to download it, I'm going to upload it to GitHub and put a link in the description. You can think about ways to improve the program. There's still a lot of stuff that you can improve, that you can try out, play around with. Maybe I did some mistakes or did some things that are not ideal, and you can improve on them. There are certainly a lot of ways you can change the behavior, like maybe you want to increase the number of random cells that spawn at the beginning, so you can find the right location in the code, change it, and try it. Then you get more generations. Maybe you want to print the count of the generations somewhere. You can do that also with tcell and maybe render a number somewhere here at the bottom that's showing, okay, this is now generation 900, 901, 2000, whatever, so that you know how many iterations it ran. Coloring, maybe you want to have a different representation. There are a lot of alternative rules for Conways Game of Life. For example, when we calculated the number of neighbors, living cells and neighbors, we handled the edges like there is no more neighbor at the edge, right? You could also say that once we are right at the edge of the screen, like here in the upper left, you can say that neighbor cells are at the opposite edge of the field. So it's basically like a game where you enter the screen on the right side when you exit it on the left side and the other way around. So that's an alternative to the existing rules. I'm pretty sure there are also descriptions of alternative rules and implementations in the internet. Like here, there's variations that you can do. Here's even an example of shapes that are not rectangular but have more sides and stuff like that. So that's it. We're at the end of this tutorial. I hope you did get something out of it. Please let me know if you liked it or what you like, what you didn't like, what you want me to do differently. Maybe you have questions or you got some ideas for future videos, topics that you want me to talk about. Feel free to leave a comment or like this video, sub whatever you want. I hope you're having a good time learning programming, and see you soon.